Okay, in this presentation we are going to look at deriving an expression for the moment generating function of a uniform random variable. A uniform random variable being a continuous random variable. That's important. Okay, so here's the question: let x be a uniform random variable on the interval ab. Derive the expression for the moment generating function mgf of x. Okay, straightforward enough. Now, just to recap on what a moment generating function is, let x be a random variable with cumulative distribution function f of x. The moment generating function mgf of x, or f of x, is denoted as follows: mx of t, okay? And that is the expectation, the expected value of the exponential of t times x. This is provided that this expectation exists for t in some neighborhood of 0. An important little caveat, but I'm not going to deal with it in this case. We're just going to sort of look at the main formula and implement the main formula there. Now, as I said before, this is a continuous random variable. So there's two possible approaches we can take. One if this variable is a discrete random variable, not in this case, and one if it is a continuous random variable, which it is in this case. So we're going to take that second case. So how we would evaluate it is the integral from minus infinity to infinity, or applying the appropriate limits of integration as per the definition of the probability distribution of the exponential of tx times the probability density function of x, f of x dx. Okay, so that's the approach we're going to take there. Okay, so let's just a quick remark that for a uniform random variable x on the interval ab, the probability density function is given as follows: b1 over b minus a. So it's essentially a constant term as far as this integral is concerned, and it is, but the range of values is a to b. Okay, so that's important. So when we calculate, we'll start to use our integral formula here. We're going to use the limits of the lower limit of a and the upper limit of b, because that is what is relevant for the uniform distribution. So we have the integral of the exponential of tx times f of x dx. Okay, so what we're going to do there is first off put in the PDF 1 over b minus a. And because that is a constant as far as x is concerned, we're just going to filter it out in front of the interval. So we have mx of t equals 1 over b minus a times the integral from a to b of the exponential of tx dx. Okay, so that is straightforward enough. This is a straightforward integration of an exponential term that we have to do. That is the general expression for that integral is the integral of the exponential of tx dx equals the exponential of tx divided by t. Okay, so just the general rules of integration and differentiation are necessary here. You have to have them at hand. You have to, in your mind, just get ready to use them. So essentially, we're ready to go. What we have to do here is just apply the limits of integration from a to b. Okay, and remember we have that constant term 1 over b minus a. So essentially we just start to piece it all together here. 1 over b minus a times the exponential of tx divided by t evaluated between a and b. Okay, so we have 1 divided by b minus a times the exponential of tb divided by t minus the exponential of ta divided by t. Okay, and we could just simplify that, and we get the mx of t equals the exponential of tb minus the exponential of ta divided by t times b minus a. And that is us. That's as far as we can go with this expression here. Okay, so yeah, we'll leave it there.